Question 3, Part A. Calculate the flux linking one turn of the coil. So let's remind ourselves of the equations that we've got. Flux density is equal B is equal to flux divided by area, and remember that will also be measured in Tesla, so Webers per square meter or Tesla. So flux density is the term we're using for magnetic field strength. So then the flux through a loop, through a turn, through a coil, is equal to the flux density times the area. So let's come back over here. We want to know the flux linking one turn of the coil. So flux is equal to the flux density times the area. And remember, when it comes to area, we've got to make sure we're using meters and not centimeters. I like it that this one has actually reminded us of that, because I think it's a shame when we get the answer wrong just for something trivial like that. So flux density is equal to flux density of 2.3 Webers per square meter times the area, and the area of a circular coil of radius, this is pi r squared, times pi times radius squared, 0.64 squared, and that one is going to equal 3.0 Webers. And remember, two significant figures, 2 and 2. So our answer is going to be in 2 significant figures. Okay, B, calculate the total flux linking the coil. This represents the flux through one loop, and we've got 21 loops, 21 turns. So the total flux, we may write like this: total flux is equal to the flux through one loop, times the number of loops. So that's going to be equal to 3.0 times 21, which equals 62 again. Weber is our unit for flux. Number 3, the coil is now rotated until its plane is parallel to the flux, and it takes 0.31 seconds for this rotation to be carried out. Why is the total flux linking the coil now 0? So this here, A, is the situation initially where our loop was perpendicular to the magnetic field. So again, we've got flux is equal to B times A, the flux density times the area. So we can see we've got this area here, which is linking the magnetic field. And in this situation now in part C, the coil is now rotated and its plane is parallel to the flux. So here it is, our coil now is parallel to the flux, and so we have no cross-sectional area linking the magnetic field, the magnetic flux. So why is the total flux linking the coil now to 0? And I think the textbook gives a pretty good answer. If the plane of the coil is parallel to the flux, the area of the coil through which the flux can link is 0, and so the flux is 0. So that's our explanation. That was just from the back of the book. Part 2, calculate the average voltage induced in the coil while it's being rotated through this turn. So it's being rotated from perpendicular to parallel, so that's 1/4 turn. 1/4 turn, and it's taking 0.31 seconds. So what equation do we have that we can use for this? Number 4 here. the average voltage V, sometimes we write the EMF rather than the average voltage, but the voltage is equal to negative N delta flux divided by delta time. Remember, the negative sign as a result of Lenz's law will tell us the direction of the voltage, direction of the induced current. N, the number of turns or loops in the coil, and this expression delta phi over delta T is Faraday's law. So we've got this equation here. The voltage is equal to negative N delta phi over delta T. To calculate the average voltage, the voltage is equal to negative N delta phi, the change in flux, divided by the time. The total change of flux, N times phi, is 62, and the time is 0.31 seconds. So the voltage is equal to 200 volts, and that's to two significant figures. So that's the answer to that. You can see they're pretty simple, pretty straightforward. Okay, there we are.